Welcome, this is day 50 here in physics. Today, we're going to be discussing, or heading towards really being able to discuss, get a pencil out here, find it here again, 3.3 here. This is where we're going to be heading towards. Use the kinetic theory to explain that the transfer of heat occurs during a change of state. Well,
Mr. Mevett, contact the office for a phone call, please. Mr. Mevett, please contact the office for a phone call.
For us to be able to discuss that change of state, we have to be able to, again, let's just do a real quick review here of heat transfer, because it's this transfer of heat that allows for there to be a change in state, or for there just to be a change in temperature. And almost all the time, not all the time, but we have three different methods. There's only three ways. The first one is conduction. Conduction is by things touching, by direct contact. This would be like your hand touching an ice cube. We had convection, as we discussed in our day 49 notes, that convection was the flow of heat or fluids, the flow of heat through fluids. It'd be like your gas-forced air in your house or furnace. And then radiation was the heat transfer of heat through straight lines. And we said everything gives off heat, specifically the sun was the best example we had of that. And we also talked about how black is going to absorb all light, thus it's going to warm faster. And that white reflects all light, so it's going to take a lot more time for it to absorb that energy. Let's get into specific heat. And the specific heat, we're going to be using this equation up here quite a bit. And let's define these terms here. Obviously, this delta, this triangle stands for delta, which means the change. So what we're saying here is there's going to be this change in heat, right? Because H is the heat or the energy gained or lost. So the change in heat or change in energy that's gained or lost is going to be proportional. This little symbol here means proportional. It's going to be proportional to the specific heat of the material times the mass of the material times the change in the temperature of the material. Now, let's talk a little bit more here about C, specific heat. Specific heat is very well related to, let's talk about the sand on a beach and the water. Well, so let's say I have the sand. We've got this beach here. All right, so we've got the sand. And then you've got the water that's coming up here. On a very hot day, if you're on vacation and you go up to the sand is going to be just really, really hot. Really, really hot, putting off all this heat. And it's going to be very hard to walk on, possibly, if you have bare feet. Whereas if you get into the water is going to seem cold, very cold still. Why is there this difference in the temperature? They both have the same sun pounding down on them. And what that comes down to is C, their specific heat. Specific heat really pertains to how much energy it has to take in before you can see a temperature change. The sand takes very little energy, and it heats up very fast. Whereas the water, it has to suck in a lot of energy before you see a noticeable change in the temperature of the water. So sand has a very low specific heat, so C would be a very small number. And the water over here has a very high specific heat, and it's going to be a very large number for C. Temperature and internal heat. Well, a change in temperature means an increase in internal energy. The molecules are going to be moving faster. The hotter something gets, the more energy it has. The more energy it has, the more kinetic energy we're going to have with the molecules. As things gain energy, they're going to move faster. As they move faster, they're going to heat up. So it's that gain energy creates the particles to move faster, their velocity increases, and as they move faster, they're right up next to each other, so they're vibrating faster, and there's more friction, so there's going to be more heat. So a change in heat means there's going to be a change in temperature. The more mass, however, necessitates more internal energy to increase the temperature. So, for example, it's just like, let's just talk about the water. It takes a little bit of heat to raise the temperature of a little bit of water. But if I have a huge amount of water, like the ocean, it takes a whole lot of heat or a whole lot of energy to raise the temperature because it has a large mass. And then the last thing that we want to relate here, the last step, is that the change in heat is also proportional to all three of these, meaning we talked about the change in temperature because of the energy, the particles moving faster. We also have the mass, such as the ocean versus a cup of water. It's going to take a whole lot more energy to heat up the ocean than it does a cup of water. The last thing, then, is C, the specific heat. This is the last factor in deciding how much energy it takes. Some materials, as we said, take more energy, such as water. Some materials take less energy, such as the sand. You can have an equivalent amount of sand and an equivalent amount of water, so their masses are the same, but their C, the specific heat, would be the one thing that's still different between the two. The sand is going to heat up, have a much greater change in temperature, given the same amount of energy. Given the same, and that's important here, that we understand that it's the same amount of energy that's given to the water, the same amount of energy that's given to the sand. The only difference here now is the specific heat, because we said they're getting the same energy, they have the same mass, so the only thing that's different is the specific heat. That's going to give us a large change in temperature. This is part one of our notes. I'm going to stop right here, take a break, and we'll come back with part two.